on gas stoichiometry. Today, what we're going to be learning about is a little bit of a connection between properties of gases and the types of conversions we've been doing using chemical equations. Gases have some interesting properties in that, regardless of the type of gas, they exhibit similar properties under similar conditions. So, we're going to learn about 4 different measurements of gases we can take, understand a constant between them, and then be able to connect that to moles, which allows us to use that in stoichiometry calculations. So think about your whoosh bottle demonstration. We did it twice and we noticed that they didn't behave the same way each time because there was a difference in the limiting factor. In the first one, you ran out of your ethanol first, but because of the gases that are created, it took up space and it wasn't all oxygen in the whoosh bottle anymore. So the second time, the oxygen was actually the limiting factor. Now, when we think about gases, one of the things that they do is exhibit pressure. So we could maybe take a look at and decide, hey, as this gas is being produced or used, how does that affect the pressure inside the container? So what's going to happen as those molecules are moving around? PIVNERT, or PV equals nRT, is the ideal gas law, and it relates all of those properties to a constant. So the 4 properties that we can measure are pressure, volume, oops, sorry guys, our pressure, volume, amount of gas, which we measure in moles, and the temperature. All of this goes back to the idea that gases can be expanded or compressed. So because the particles of gases are so much further apart under normal conditions than solids or liquids, there's a lot of room between them. So because of that, we can compress the particles closer together. So one of the things that we're going to take a look at, I don't know why that 2 is there. All right, there we go. So we're going to take a look at the different measurements of these variables and how you might see them presented in a problem. So within the ideal gas law, pressure is often measured in atmospheres or millimeters of mercury. Whoops, that should be a lowercase g for sure. So millimeters of mercury is a common measurement. They used to have a literal tube with mercury in it that would change based on relative pressure. Because of the constant that we're going to be using, we have to convert all values to atmospheres when using PIVNERT. The volume has to be in liters, so you might see in a problem that it's given in milliliters or some other metric unit. We're not going to do anything with standard, but we have to get it to liters. Number of moles can be converted to from mass if it's provided, but we use moles for lowercase n here. Notice that's the only lowercase letter in the equation. R is the gas constant, and this is why we have to do all of this converting. So the relationship between these 4 variables equals 0.0821 atmosphere liters per mole Kelvin. So if we use different measurements or units of pressure, volume, and temperature, we would have to use a different gas constant. Others do exist, but to simplify it, we will just always convert to these units when doing calculations. Temperature is a must. We must be in Kelvin because it ends up setting, you'll never have a measurement of 0 degrees. And because you can end up with temperature on the bottom, dividing by 0 is not a thing. We can't do that. Kelvin set 0 as to absolute 0 or the absence of motion. So we're going to see just a moment for how to convert that. Now with gases, many conversations happen around a specific set of temperature and pressure. And when we look at that, 0 degrees Celsius is equal to 273 Kelvin, and that is the standard temperature. The standard pressure is 1 atmosphere. One of the things that's been determined for 1 mole of any gas, so remember we said unique property, regardless of the type of gas, any gas at standard temperature and pressure will have a volume of 22.4 liters if there is 1 mole of particles. So all gases exhibit similar behaviors under these conditions. Notice we have an equivalency. 1 mole equals so many liters. That could potentially be a conversion factor in the future. So what conversion factors might you need to use? For pressure, the relationship between atmospheres and millimeters of mercury is 760. Just a reminder of the conversion from milliliters to liters. This is one you should know, but 1,000 milliliters equals 1 liter. At STP, remember we said that is 273 Kelvin, which is the same as 0 degrees Celsius, and 1 atmosphere of pressure. That 22.4 liters of a gas equals 1 mole of a gas. When having to convert to Kelvin, it's a pretty simple conversion. We simply have to add 273 to the value for the degrees Celsius. So let's say I wanted to convert 25 degrees Celsius to Kelvin. I would simply add 273 plus 25. So that would give me 298 Kelvin. And notice there's no degree sign used with Kelvin. It's just a capital letter K. So what does a problem look like if I need to calculate with Pivnart? Let's practice our annotating while we read the problem. So at 34 degrees Celsius, data point, and I'm going to label that T for temperature. The pressure, here we go, inside a nitrogen-filled basketball with a volume of 7.60 liters, okay, so that one's V, is 2.0 atmospheres. That's a pressure. How many moles, okay, here's what we're solving for. That's what we want to find, of nitrogen gas are in, forgot to change that part, basketball. If you are curious for some additional support on this type of problem, page 465 in your textbook has more information. So let's consider what we know. We know temperature equals 34 degrees Celsius. We know our volume is 7.60 liters. We know our pressure is 2.0 atmospheres. And we know what we have for Pivnart, that R equals 0.0821 atmosphere times liters over mole times Kelvin. Okay, so we have to remember, even though this isn't given in the problem, this is a known variable. What we don't know, we'll change color here, is the number of moles of gas in the basketball. So that's what we're trying to determine. So the first thing that we're going to do is we're going to write down our equation and then start plugging in our variables that we know. So I've got PV equals nRT. My pressure is 2.0 atmospheres. My volume is in the correct unit of liters. And notice that atmospheres was also my correct unit. N is what I'm solving for. I've got my 0.0821 atmosphere liters per mole Kelvin. Now you won't have to necessarily write this unit out every time, but I'm putting it in this time so that we can see how the units cancel. Now my temperature is in Celsius, and we said that we need to convert that to Kelvin. So I'm going to add 273. So that should give me 307 Kelvin when I do that. So I got my K there. So now to get N all by itself, I have to divide both sides by what it's multiplied to. All right. So this side totally cancels out, right? This side, let's see what happens with that unit on the constant. All right. So we've got the liters canceling out here. We've got atmospheres canceling out here. Remember that when I have a compound fraction, what's on the bottom of the bottom is actually like multiplied by. So this is technically like being up here. So I shifted this. We're just going to take it out completely. Notice that the Kelvin cancels out, and that leaves moles is the only unit I have left. Why is that good? Because moles is what I'm solving for. So if we type this all in the calculator, our final answer, N, number of moles, is going to equal 0.60 moles of the nitrogen gas. Okay. So it's really just a plug and chug equation. I just wanted to be able to show you guys how the units cancel out, but really what's happening is the constant brings all of those units together. And so whatever you're solving for will be the unit on your final answer. So let's take a look at what we have next. So imagine we could look into that basketball, and what we would see is we'd have all these different gas particles moving around within the space. So for the 7.6 liters that we had at 2 atmospheres of pressure and a temperature of 307, the 0.6 moles is what would equal my total particles that meet those conditions. So the constant R that we use, that 0.0821, this is what links all 4 of those variables together. So as long as we know 3 of the variables and our R, we can solve for any other unknown. So let's try a new problem that instead of solving for moles, we solve for something else. Let's say the gas cooled to 10 degrees. Here, we'll box that. That's my new temperature. Because I went outside to play, temperature was lower. What would be the new pressure? So this time we're going to solve for pressure. Inside the ball B, what would it be to maintain the 7.6 liter volume with 0.6 moles of the gas? So we had that same sample of gas. So my temp equals 10 degrees Celsius. If I add 273, that gets me to 283 Kelvin. My volume is still 7.60 liters. My pressure is unknown. That's what I'm solving for. And my number of moles equals 0.60 moles. So plugging into my equation, P is what I'm solving for. Multiply that times my 7.60 liters equals 0.60 moles times 0.0821 times my 283K. So I'm going to divide both sides by 7.60 liters, cancels this part out. And my pressure is equal to 1.8, which is our sig figs because I only have two there, atmospheres of pressure. Notice that means my pressure went down when the temperature went down. So that kind of makes sense because that cools the motion of the particles. They're not moving as quickly and therefore not applying as much force on the inside of the ball. Later, you're going to do some activities exploring these relationships a little bit more in detail. So how could we connect this to a stoichiometry problem? Let's consider for a moment that we did a reaction between magnesium and hydrochloric acid. You've done ones like this before. If you recall from our guided types of reaction lab, this is where you did the burning splint test and got that pop that confirmed that hydrogen was produced. Well, hydrogen is a gas, so it's one of these gases that behaves under these conditions of Pivner. So what we could do is running the reaction, we could actually collect it by bubbling it through a tube and then getting, excuse me, that gas sample into a container to trap it. That would allow us to do some measurements. So let's consider that we started with 45.6 grams of the zinc and reacted that with the hydrochloric acid. So that's my starting value. Then it says to determine the number of moles of the hydrogen gas produced. I should have boxed hydrogen gas too. So I'm starting in grams of zinc, and I want to finish in moles of H2, which means I'm going to have to get to moles of zinc first to do that. So we're going mass to moles and then moles to my new substance. So I'm going to start with my 45.6 grams of zinc, multiply that by 1 mole zinc over my molar mass, which is 65.39 grams of zinc. Now I need my mole ratio to get to hydrogen. I see in my problem that I have only 1 mole of H2, but that's also in a relationship up to 1 mole of zinc. So I have canceled grams of zinc. I've canceled moles of zinc. Now I'm in moles of H2. So I would take my 45.6 divided by 65.39, and I have, including my sig figs, 0.697 moles of H2. Now, so far, with the way the problem is worded, I haven't had to do anything fancy yet. This is what we've always done before. But the next step we're going to look at is like, okay, now that I know how many moles I have, how could that relate to calculating one of the other gas variables? Let me clear the page here. All right, so just a quick little what's going on here. So let's say that we put that metal into the acid. What's really happening is that your did I flip my ones here? No, I did not. So you would have the H plus ions that are in solution. Let's just reiterate those. So these guys were coming in as separate H plus ions. I was having trouble capturing exactly what I wanted. And I would have Cl minus floating around in the solution. That was my HCl, right? So what happens is the H plus is going to pick up some electrons from the zinc. Remember, zinc is a metal and it very readily gives up those electrons. That's a property of metals. So when there are two H plus ions present, they can pick up the two electrons that are given up by the zinc and then they can form an H2 molecule of gas. And this is what's going to leave as the H2, and that leaves behind the zinc ions that are now dissolved in solution and no longer a part of the solid structure. So what we see in the reaction is bubbles form, which is the formation of the H2 gas, and then what's left behind is the zinc chloride that's left over. So now let's take a look at our problem. It says in the reaction, we started with our 45.6 grams of zinc. I added that to the hydrochloric acid, but this time I want to determine the volume of the gas produced at a temperature of 20 degrees Celsius, that's my T, and a pressure of 765 millimeters of mercury. So remember that we figured out that the moles of H2 had equaled 0.6, hold on, 97 moles of H2. So at this point, I am presented with a temperature. I have a volume that I want to solve for. I have a pressure of 765 millimeters of mercury. And my moles are known from my problem at 0.697 moles. So through the Stoich, I did the conversion to calculate moles. Since I know moles and I know three of the other or my other variables, I can solve for volume using Pivnert. So I'm going to convert my pressure to atmospheres because remember that we need to use that for the conversion or the R value. Our conversion factor is 1 atmosphere equals 760 millimeters of mercury. That's going to give me really close to 1. Gives me 1.01. So almost 1. I have to add 273 to get to Kelvin, so it gives me 293 for my temperature. So new color just to make it easier to see. My pressure is 1.01 atm times the volume that I'm solving for equals 0.0, sorry. Need my eraser here. Apparently the eraser doesn't like to go, so we'll just go back to pen tool. Oh no. It erased all my work. That's never good. So let's try this again. We'll just go from here. So my pressure was 1.01 atm times the volume I'm solving for equals 0.697 moles times 0.0821 for my constant times my 293K. Sorry that cleared the screen. So we're going to divide both sides by 1.01 atmospheres. Notice me showing all my work with units. Cancel atmospheres over here. All of this will cancel out except for my volume unit. So I'm going to get a volume in liters, which is 16.6 liters. So as long as we can get to moles through a stoichiometry problem and we're provided the other variables in the data for temperature, volume, pressure, or whatever, we can figure out that remaining variable using Pivnert. So what you're going to do next is you're going to move into practice where you'll get to do some simple conversions with some of our pressure, volume, and temperature units. We will then do some PIV-NERT problems with just the equation of PV equals nRT, and then you will get to do some additional practice problems with gas stoichiometry. Please be sure to stay on top of checking your answer keys and seeking help as needed.